Let's begin by reminding ourselves about this diagram that we've seen before. We know the natural numbers lie inside the integers, which lie inside the rational numbers, which lie inside the real numbers. But we can extend this even further to include the square roots of negative numbers and numbers of the form a plus b times the square root of a negative number, where a and b are real numbers. So these are what's called the complex numbers, and that's the subject of chapter 1. So if we think about the equation x squared plus 1 equals 0, and if we want to solve that equation, we would first move minus 1 to the other side, and then we would try and take the square root. But the problem is we know the square root of minus 1 isn't a real number, because we know the square of any real number is always at least 0. But we can get around this. If we let I be the square root of minus 1, then we can say the two roots of this equation are plus and minus I. So the complex numbers, which are denoted by C, like this, the complex numbers are just the set of a plus bi, where a and b are real numbers. So a number of this form a plus bi is called a complex number, and a number of the form bi, where b is a real number, is called an imaginary number. So, and this set is called the set of all complex numbers. So complex numbers are really useful to help us solve equations that otherwise we couldn't solve, because they're equations that have no real solutions. So let's just first do some things with I. So if we have this question to simplify the square root of minus 50, we want to write our answer in terms of I, we could just start by using the laws of surds. So minus 50 is the same as 25 times minus 2. So that's root 25 times root of minus 2, which is 5 times the root of minus 2, which is 5 times the root of 2 times the root of minus 1. So it's 5 root 2i. So in order to simplify the square root of a negative, to write it in terms of I, first imagine the negative wasn't there, and simplify that, and then multiply by I. And then we can add and subtract complex numbers, numbers that are in this particular set. So if we have two such numbers, a plus bi and c plus di, we add them in the way you think we add them. We add a and c, and we add bi and di to give us b plus di. And we can say, if we have a complex number of the form a plus bi, a is called the real part of the complex number, and b is called the imaginary part. So to add complex numbers, we add the real parts and we add the imaginary parts. And similarly to subtract, we do exactly the same kind of thing. We subtract the real parts and we subtract the imaginary parts. So for example, if we want to subtract 3 plus 6i, if we want to take away 2 minus i from 3 plus 6i, we do 3 minus 2 to give us 1, and 6 minus 6i minus minus I is 7i. So that's the answer. So we can now solve every quadratic equation over the complex numbers, because every quadratic equation has two real roots over the complex numbers, or possibly a repeated root. So if we want to solve the equation z squared plus 200 equals 0, and by the way, we often use the letter z to denote a complex variable, just like we often use x to denote a real variable. But the reason I prefer to write z like this, with a line through it, is so that I don't confuse it with 2, because often if you have something where you have 2z squared, or you have a lot of 2's and z's, then it's easy to get confused. So we have z squared plus 200 equals 0. We can rearrange that to give us z squared equals minus 200, and then we can take the square root. So z is plus or minus root of minus 200, which is plus or minus 10 root 2i. Okay, and then part B, there are a couple of different ways we could solve this. Factorising is generally quite difficult over the complex numbers, so we won't try that. But possibly the easiest way is just to use the quadratic formula. So by the quadratic formula, z is 6 plus or minus the root of 6 squared minus 4 times 1 times 25 over 2 times 1. So notice now the thing inside the square root, the discriminant is negative. So obviously there aren't going to be any real solutions, but there will be two complex solutions. So if we simplify this, 36 take 100 is minus 64 all over 2. So 6 over 2 is 3. And then root 64 is 8. So this is going to be 8i over 2, which is 4i. So the two roots are 3 plus minus 4i. We can also multiply complex numbers, and the key property to use to multiply complex numbers is the fact that I squared is equal to minus 1. So if in general we take two numbers a plus bi and c plus di, and we multiply these together, we can expand the brackets, so we get AC, and then we get bi times c, so that's bci, and then we get a times di, that's adi, and then we get bd times I squared, but I squared is minus 1, so this becomes minus bd, so we get ac minus bd plus bc plus adi. And this is the answer. So we can use that to multiply complex numbers. If, for example, we want to express, we'll do part 2 of this question, express in the form a plus bi, where a and b are real numbers, 3 minus 2i all squared. So if we take 3 minus 2i squared, well, if we were to expand the brackets, we would get 9 plus 4i squared, and then minus 12i. But notice that 4i squared is minus 4, because I squared is minus 1. So this is 9 minus 4, that's 5, minus 12i. We can also look at powers of complex numbers. First, let's just consider I, powers of I. So we know I to the power 1 is I, and we know I squared is minus 1. But how about I cubed? Well, that's I squared times I, which is minus 1 times I, which is minus I. How about I to the 4? Well, that's I squared squared, which is minus 1 squared, which is 1. How about I to the 5? Well, I to the 4 was 1, so if we times by I, we get I. Then I to the 6 is going to be the previous thing times I, so that's I squared, which is minus 1. And we can keep going, and we'll find that this pattern of these four values, I minus 1 minus I1, repeats itself over and over again. So if we want to work out something like I to the power 2020, well, we know that this is a multiple of 4, so it's going to be 1. If we had something like I to the power 4057, that's slightly more complicated. We have to think about how that's related to a multiple of 4. So we know that 4056 is a multiple of 4. This is one more than 4057 is one more than a multiple of 4, so this is I. Next, a definition. So given a complex number z, which is a plus bi, where a and b are real numbers, we define the complex conjugate of z, denoted by z star, to be a minus bi. So to work out the complex conjugate, we just change the I term to be minus what it was previously. So the conjugate of 1 plus I is 1 minus I, the conjugate of 3 minus 4i is 3 plus 4i. And some people write z bar for the conjugate. Usually I write z bar, but in the book and in the exam they'll use z star. So let's just have a think. What happens if we work out z times z star? Well, that's a plus bi times a minus bi. So we get a squared minus b squared I squared. But then I squared is minus 1, so this is just a squared plus b squared. So this is kind of interesting because it's related closely to another concept, which is that the modulus of a complex number, so if we have a complex number z equals a plus bi, the modulus of z is the square root of a squared plus b squared. Or said differently, so this is equivalent to saying that the modulus squared is z star, because we know z star is a squared plus b squared. And let's also work out z plus z star. So that's a plus bi plus a minus bi. Well, that's 2a. That's a real number. So if you add a complex number and its complex conjugate, you always get a real number. And if you subtract, we have a plus bi minus a minus bi. That's 2bi, which is a purely imaginary number. So if you subtract the complex conjugate of a complex number from the complex number, you get an imaginary number. And we can use this to divide complex numbers. So if we wanted to work out, let's say 5 plus 2i over 3 minus I, and we want to write this in the form a plus bi, where a and b are real numbers, then we can do something quite similar to when you rationalize the denominator of a surd. We need to multiply by something that gets rid of the 3 minus I in the denominator here. And the thing to multiply by is going to be the complex conjugate, because we know when we do that, we're going to get a squared plus b squared, which is a real number. So we can eliminate this from the denominator by multiplying by the complex conjugate, which is 3 plus I. And then in the denominator we've got 9 minus I squared, which is 10. So we have this. And then we just need to expand the brackets in the numerator. So we get 15 plus 6i plus 5i plus 2i squared all over 10. And then 2i squared is minus 2. So we get 13 over 10, or 1.3, plus 11i over 10, or 1.1i. And that's the answer.